Thank you for inviting me today. So I'm going to present you some work today, which is slightly different from what you saw in previous presentations yesterday and this morning. It involves a form of AI which is not infused yet with statistical machine learning. So I'm going to spend some time presenting the general philosophy and mathematical formulation. So basically, yes, inspired by Isaac Asimov's laws of robotics. So I will go through a very quick introduction. Isaac Asimov was professor at Boston University in biochemistry, but he was also the first to foresee that there would be a science dedicated to robots at a time where robots were still a matter of pure fiction in 1941. So he unknowingly actually invented the word robotics to describe this science, this future science at the time. So he was the first one to think through the logic that must be programmed in robot behaviors. And in this way, in my opinion, we could consider him as the first roboticist in human history. So his main idea was that we need to be able to trust robots. And to do so, he proposed that they always obey three laws that we just follow. So first law, a robot may not injure a human being or through inaction, allow a human being to come to harm. Second law, a robot must obey orders given it by human beings, except where such orders would conflict with the first law. And third law, a robot must protect its own existence as long as such protection does not conflict with the first or second laws. So ideally, a robot would satisfy all three laws, not injure human beings, obey orders, and protect its own existence all at the same time. So these laws could be contrasted with the Decalogue from the Bible. You shall not steal, you shall not kill. But here, the main point is to prepare for situations where these objectives might conflict and to propose a guidebook, strict rules to deal with such conflicts and degrade objectives in a fixed, controlled way. So why is it important that we are able to trust robots? I would like to show a couple reasons. If we want our robots to assist us, they will, I believe, realize their full potential only if they come closer and closer to us and stop staying at a safe distance as they do currently. So they can even become part of our own body, as we can see in this example, that we need for our everyday life. So here you see this person has a robotic ankle and foot prosthesis, which is actively helping her to move, walk, and dance. So I believe you really want to be able to trust such a robot part of your body. Here's another example. If you want robots to realize their full potential, they will also become increasingly dangerous. So I happened to work on this example recently. It's a fully autonomous transit bus. It will be tested in the streets of Paris by the end of this year. I mean, this is happening now. This robot weighs 40 tons and carries up to 100 passengers. So that's 100 people inside the bus and even more people outside the bus. That could be at risk of very serious injury in a matter of a split second if anything goes wrong. So once again, I think you want to be able to trust that robot as well. Now, if we focus on this bus example, a specific issue with transit buses is that passengers don't have seat belts, and some passengers don't even have seats. So, and you have to know that there are more deaths in France due to people falling in everyday life than deaths due to traffic accidents. Falls are more lethal than traffic accidents overall. So in the case of the bus, strong decelerations can make passengers fall, what can be lethal. So the bus has to be particularly careful about that. So here what could be an adaptation of Asimov laws or formal laws for bus driving. So first, a bus may not injure its passengers. You have to be very careful about that. A bus must not collide its environment. That's pretty standard. And of course, the reason to use a bus is that it follows its itinerary and timetable. So these laws can be formulated mathematically as follows, very, very simply. You will have a maximal deceleration to not injure your passengers. You will have a minimum distance to obstacles to not collide. And then you would have a desired velocity to follow itinerary and timetable. Now, the obstacles in the environment of the bus on the second line might be humans. So if there is a conflict between the first and second laws, between the maximum deceleration and the minimum distance, it would mean a choice has to be made between injuring people inside or injuring people outside the bus. You could see this as an ethical dilemma in itself, but there are actual regulations on maximal deceleration for public transports that must not be transgressed. These are regulations. So in case of conflict, these regulations impose that we degrade objectives in the following way. The bus may not injure its passengers. You have this maximal deceleration limit, which is imposed. It cannot be transgressed. And then the bus must not collide its environment, but if there is a conflict with the first law, well, it comes second. And then third law, following the itinerary timetable is fine, but just as long as it does not conflict, of course, with the first or second laws. So there would be interesting implications to explore here, if you want, maybe in the question session, but let's continue with this ordering. So this degradation of objectives following a strict order can be formulated mathematically as a sequence of optimizations. On the first line, we have the maximal deceleration limit that we don't allow transgressing. It's a hard constraint. On the second line, we allow transgressing of the collision avoidance. So the minimal distance to obstacles can be violated by a positive amount, V. But we want, however, to keep this violation as close as possible to zero. So we have this minimization, this first minimization here. And in the end, we want to follow the desired velocity as closely as possible. So in the third line, we have this second minimization. Ideally, of course, the violation V is equal to zero. So collision avoidance is fully satisfied, and the velocity of the bus follows the desired schedule. So this sequence of optimizations can be approached alternatively as a lexicographic program. Here, what we do is that we remove the minimization from the second line, we just keep the constraints, and then on the third line, we say, hey, no, we let's minimize V and x dot minus x dot desired. That means basically the same thing. We first minimize V, and then we minimize the difference between actual and desired velocity. The point is, in doing so, is that a lexicographic program involves multiple objectives. Here you have V and x dot minus x dot desired, but it can be approached as a single optimization. This is done by using a single total order over the whole set of objectives. So if you want to compare two sets of values, here you would have V1 and x dot 1 on the left and V2 and x dot 2 on the right. What you would do is that you compare first V1 and V2. And if they are, one is smaller than the other, then you are done comparing. But if they are equal, then you would compare the second objective here. Okay, so x dot 1 and x dot 2. So it's just like how you order words in a lexicon. You compare first the first letter. If they are different, then you're done comparing. But if they are equal, then you compare the second letter. And that's how you order words. And then that's why we call this order lexicographic order. So using this single total order, you can adapt any classical optimization algorithm to solve this lexicographic problem, at least in theory. You can even, in theory, use Lagrangian duality. But it's not without issues, and we will see that later. Okay, so far we have this lexicographic program to consider, but we don't want these properties of maximum deceleration, minimum distance, and desired speed to hold just at a single instant. We want them to hold globally at all future time. So instead of minimizing objectives at a single instant, we consider integrals starting at the current time and with no ending time, like that. Okay, so we have these infinite integrals. In that case, there is, of course, the issue that we can't know what the environment of the bus is going to be like more than a few seconds in advance at best. So to make sure that these properties hold globally at all future time, we borrow from model predictive control theory the key concept of imposing a terminal constraint. So this terminal constraint, in that case, is one we naturally apply when we draw in fog. Let's see how it looks. So here, The desired speed for the bus is 40 km per hour, which is approximately 11 meters per second. So starting on the left at this speed, if the bus can't see beyond a certain distance, we know that it can safely maintain this speed for, here in this example, a couple seconds. And then it will have to slow down at maximal deceleration and come to a stop within the limits of the current field of view, because it doesn't know what may lie beyond. So the terminal constraint here is to be able to stop within the limits of what the bus can see, of what the bus can reasonably anticipate. And if the bus maintains a zero velocity after having stopped and stays there indefinitely, we know that zero deceleration will not injure passengers. And we know that the distance to obstacles in the environment will be kept constant, at least if the environment is static. So we can validate, as a result, that with such a plan, the bus can satisfy the first two laws and maintain safety indefinitely. Concerning the third law, let's have a look at what happens when the bus moves forwards. Okay, so we had the plan, which is now in a dotted line, and we move forward. After a second, the field of view extends further down the road. So we may know that the desired velocity now can actually be maintained for yet another couple seconds, because the bus can actually stop a little bit further down the road. You know, as you move forward, you can see further down, and you can make sure about your motion a bit further. So you can calculate that every second, the next second, and next second, so that ultimately the bus can continuously follow the desired velocity without any real interruption. So the terminal constraint here just provides the guarantee that it is always able to stop safely within the limits of the current field of view. So you end up solving periodically this lexicographic program with a terminal constraint. Each time you take into account the actual current state of the system and environment. So this is a very generic approach that we have used here for this bus, but also with human robots and collaborative industrial robots. Every time it's with different constraints and objectives, but using the same methodology. Now, if the environment is not static, so here if you have the obstacle moving as a function of time, collision avoidance is not guaranteed. Okay, but still you can keep the same terminal constraint, which is to stop within the limits of the field of view. Because in that case, if an obstacle moves and collides with the bus afterwards, at least the bus is at rest at the time of collision. So in a way, the robot does not collide, it is collided. So this is called passive motion safety, and this is a standard safety guarantee in the field of autonomous vehicles. But if the environment is not static, we also need a way to predict its evolution in the future. There are different ways to build such predictive models, but a crucial property for safety is to be conservative with respect to the uncertainty of the environment. This uncertainty appears here as an additional fog, as I used this image earlier for the terminal constraint, establishing places which are potentially unsafe, and therefore that the bus must avoid until we can see more about what's going to happen. A common issue, however, is that this model can be too conservative, to the point that it leaves no visibly safe motion for the bus, and the bus would completely stop moving as a result. So one option to reduce conservativeness is to develop a more precise predictive model. And to do so, actually one of the key aspects to adjust for the bus is that the behavior of the obstacles here in the environment might depend on the actions of the bus itself, okay, on the current speed and acceleration and future speed and acceleration of the bus. And if we want to account precisely for such action and reaction groups, this program becomes hugely expensive to solve and definitely not something we can do online. Okay, so you could think of solving this problem offline then, using some form of deep reinforcement learning. So here I just pulled an example paper published earlier this year. So it's kind of the current state of the art. I reproduce here typical simulation results, where you have multiple agents, each one with a different color, and they have to switch positions. They all use the same optimized policy, okay, which was then found using deep reinforcement learning. And they all use the same policy in the same simulated environment. So there is no remaining outside uncertainty. And yet, they report in the paper that there are still collisions happening every few minutes of simulation, because the policy they obtain is, of course, suboptimal. It's approximate. And you can certainly not accept that a bus driving in city streets will have collisions every few minutes. So having such an approximate solution is not acceptable. So it seems to me that if we want to guarantee safety, currently our only option is to solve this problem online, as I showed earlier, with simplified conservative models of the environment. And this paper I'm showing here was not even addressing a lexicographic program. You had just a single objective, go there and avoid collisions. And lexicographic programs, as I introduced earlier, they can be even trickier to solve. So in order to quickly show you why this can be tricky, let's consider probably the simplest possible example, at least the simplest I could imagine. So you have a mechanical system with just two articulations and two straightforward objectives. You have a round moving base, which can move left and right, x, coordinate x. And then you have a rotating arm with an angle theta. And then you want that the end of the arm, so coordinate would be x plus cos theta, reaches an object 2 meters in front. So we want this function g here to go to 0. At the same time, you have this second objective that the base of the robot stays at the origin. So you want f, which is equal to x, to stay at 0. And since the length of the arm here is only 1 meter, you can't do both. And there's a conflict. Okay, straightforward example. So here we will say that the objective to reach the target 2 meters in front with the end of the arm comes first. And the second objective is to stay at the origin, but only if it does not conflict with the first objective. So if we plot a graph with these two objective functions, f and g, along the two axes, the whole red region is unreachable because of the limited arm length. And the ideal goal would lie at the origin here, unreachable in the red region. So if the priority, as I mentioned, is to have g is equal to 0, and then have f as close as possible to 0, then the lexicographic optimum would sit at the red cross up left. Okay, so that's the optimum in the lexicographic sense. If we analyze more carefully what's happening in this graph, when the robot is in the white region, upright, it looks like in the top figure. And in this case, the gradients of the two objective functions are linearly independent. So we can find a common distance direction for both, basically oriented towards the origin. Okay, so when you are around here, then you can find a gradient going in this direction. This corresponds in the graph of the robot, the little figure, to having both the base of the robot going left and the end of the arm going right at the same time, as we would like to happen. But when the robot is on the border of the invisible region on the red line, it looks like in the bottom figure. In that case, the gradients of the two objective functions are linearly dependent and actually opposite. So you can find a descent direction only for one, not for both. And then in that case, the gradient will be oriented along the red line. So in that case, we can have either the base of the robot going left or the end of the arm going right. And if we give priority to the second objective, then that's what's going to happen. So what we can observe here is that the robot is in a singular configuration. You have linear dependence between gradients on the red line. And obviously also the optimum, which is on the red line. Okay, so here is the typical behavior that you obtain when you apply a standard gradient descent. You take the same kind of algorithm that is used in machine learning. When you start from a singular configuration, so you start on the red line, you have the yellow trace that you can guess here, and it will slowly converge towards the optimum located at the red cross. But in all of the cases, you can see that the gradients never provide a good direction. The gradients push the solution towards the origin, and then when the iterations approach the singular configurations, it starts going in the completely wrong direction. There is no convergence at all. Even so, in this simplest example, so you can expect that if you want to apply machine learning algorithms to the more complex lexicographic program that I was showing earlier for the bus, it can turn out to be very tricky to converge. And just briefly say that there are deep theoretical reasons behind this issue. The fact that this lexicographic programming involves non-strictly convex objective functions, and you have a lack of constraint qualification, which make the first order optimality conditions elusive. So a summary, because I've already said a lot, what I try to share with you today is that usually in research papers, we focus on one particular aspect, one specific issue, one objective that robots must solve, robots must face. But in real situations, robots have to face multiple, possibly conflicting objectives, not just one. And you will always be this issue if you think thoroughly through any typical real robot use case. As an example, we did work on having a biped humanoid robot moving in a dense crowd in simulation. And you can't escape the fact that sooner or later, the robot will have to choose at some point between keeping its balance and avoiding a collision. And in such a situation, either you accept one failure or the other, and you have to decide which. And there is a never-ending list of such choices that need to be made, sometimes connected to very interesting ethical questions, actually. So it is important, in my opinion, to be capable to guarantee in the long term that some of these objectives are met strictly, while others might be degraded. And you have to do that in a pretty fine way and very carefully. It is a matter of safety and dependability, and I believe I can't overstate the importance of these aspects. So all this can be approached with lexicographic multi-objective model predictive control, as I showed, but this is an ill-posed problem. So this is an approach we tested on the bus prototype I showed earlier in the video, but we didn't test it with people around, and I'm not ready to let this happen. Our current numerical methods work pretty well. I'm quite proud of what we can do, but I'm not going to put any lives at stake until all the theoretical issues that I mentioned are properly understood, and it's not the case yet. So I'm going to stop here because I believe I'm showing something quite different, and maybe you will have questions about all that. So I'm ready to answer your questions if you have any.
So thanks, Pierre-Brice, for the thought-provoking talk, and I'm sure we will have also interesting discussions at the end in the panel, I think, when we will talk about human-robot interaction and trust. I think it's a very interesting topic. I'm trying to see if, let me check the chat again. So I don't see right now any question in the chat. From my side, I had, I was triggered by your examples because that's exactly the field I'm currently working on, and the navigation, for example, in the crowd, and we have had endless discussions about how reasonable it is to learn these behaviors when we don't model the reaction of humans, or the appropriation, let's say, of humans. And I was wondering if you had, you touched briefly upon it, if you had some examples or some insights into these aspects. What is how strong or how big is this component in this kind of systems in terms of how important it is to take these into account, and what role do they play? You touched briefly upon it.
Well, I believe it is central, and it is a very difficult issue. A lot of people are working on that, and there's no definite solution so far. As I said, you have this, you have this freezing problem, which is very well documented and known for quite a long time in such situations. And if you don't want to do that, what are you ready to accept? So first question is, you would have some ethical questions, and I believe we should at least think about them. Do we accept that the robot pushes you as a person would do? You know, you're in a dense crowd, you want to move opposite direction the crowd, you have to have contact. Imagine a robot firefighter. You know, there's a fire, so the crowd is moving away from the fire, and they want the robot to go the opposite way. So of course, this is an extreme example, but you see, as I was mentioning, when we're doing these simulations of the human robots in the dense crowd, you could have the robot avoiding collisions, but because it was losing balance, so it was throwing itself on the side, it just let you pass. And even so, you might not agree with such a behavior. You might say, hey, you know, the robot stays there and braces for contact, and you run into the robot, and there's an issue. So you have questions like that which are not easy to handle, and you would have, you know, social aspects, and I like to start with that, because then of course this will define the kind of mathematical problem you want to solve. And so you have these reaction loops that I was mentioning, and that's in itself a very difficult problem. As I was showing, you have some people who propose solutions, like in the paper I just showed, but these solutions are still not reliable. It is not if you have safety in mind. So I'm glad you're interested in this topic. Maybe we could discuss this further. The bad news is that it's a very difficult problem, and I believe we are very far from having a solution to propose.
Yeah, thanks.